Well, good afternoon, everybody, and it's great that you're able to join us. We're absolutely delighted that Neil Lawrence, who is the DeepMind Professor of Machine Learning at the University of Cambridge, is coming to be our second speaker in this webinar series. I'd like to just say a little bit about the journal, just to warm things up. So the journal is dedicated to the advances in all of the engineering sciences and the engineering professions that data science, or the data sciences more generally, will have on these disciplines. And when we talk about data sciences, we are including, for example, machine learning, artificial intelligence technologies, computational statistics, applied mathematics, and so on. And one of the things I'd really like to do is to encourage you to visit our website and have a look at some of the papers that have already been published, read some of the blog entries, and of course, revisit some of the webinars that will start to accumulate. And most of all, I would really encourage you to think about submitting some of your work to the journal. So I'm going to hand over to one of our editors, Lizzie, who's going to introduce our speaker for today. So Lizzie, over to you.
Thanks, Mark. Hi everyone, my name's Lizzie Cross. I'm a professor in the Dynamics Research Group at Sheffield. Today I'm absolutely delighted to be able to welcome and introduce Professor Neil Lawrence. As Mark said, Neil is the inaugural DeepMind Professor of Machine Learning at the University of Cambridge. He's also a visiting professor at the University of Sheffield. He's recently returned to academia after 3 years as the Director of Machine Learning at Amazon. He currently holds a senior AI fellowship from the Alan Turing Institute on the interface of machine learning and systems research. I'm not going to embarrass him further by going into his many achievements and accolades, but just to say we thought Neil would be a perfect candidate to give a talk for this webinar series. And as you'll see in a minute, his research interests are about machine learning in the physical world, so it's a great fit. Before doing his PhD in 2000, Neil did a bachelor's degree in mechanical engineering, and then worked as a field engineer in the rigs in the North Sea. Since then, his work has been applied to many diverse fields, so from complex software systems to systems biology to neuroscience. Needless to say, we're really fascinated to hear his talk today and learn a bit more about his unique perspective on the challenges that we face in a data-rich world. So without further ado, I'll pass over. Neil.
Thank you very much, Lizzie, and thank you, Mark, as well, and everyone for the invite and everyone for attending. So I'm going to try sharing screen. Okay, can everyone see that? Shall I just proceed? No, brilliant. I can see the thumbs up from Lizzie. So I was really pleased to be invited to this series because I'm sort of very aware of the work going on in data-centric engineering, the Turing Institute, the Lloyd Foundation, and the importance of this interface between machine learning and what I think of as the physical world. And I'm going to try and highlight why I find that so interesting as I go through. I'm just going to pop in the chat. I've got some talk notes that I've just popped the link in the chat. They're not sort of a comprehensive piece, but there's some notes that you can read along with the slides and also see the slides yourself. So I want to start with this thing that I find very interesting, and actually I'm sort of inspired by the work of Mark and others a bit with this thinking in terms of probabilistic numerics, which I think of as emergent behavior, because I think it is so key to what we're trying to do when we're at the interface of engineering and understanding and the real world around us. And what I want to talk about first is a very artificial world. So I want to talk about Game of Life, which is this game invented by John Horton Conway, who sadly died, I think, last year. But it's a very simple game, which is played on a board, a sort of checkerboard, where you have a cell is alive if it's black in this case, and dead if it's white. And I just look at the sort of neighbors of this particular cell we're focusing on here, And at each turn, you get things happening to each of these cells. So in this case, if a cell has less than 3 neighbors, so here it's only got 2 neighbors, in the next turn it will die of loneliness. Something would also happen to the cells around it. We're just focusing on this middle cell because it's too lonely. And that's rule 1.
Neil, I can't see a picture. Should there be one?
You can see, so you don't see my slides?
I just see the black screen with the title on.
Wow. Okay, let me try resharing. Thank you for pointing that out before I completed the whole talk without anyone being able to share. Let's try that again. As a computer scientist, I started as a mechanical engineer, but I became a computer scientist when I learned you have to switch things off and on again. And then
there we go.
Yeah.
We're on the loneliness slide.
You see, switch it off and switch it on again. There we go. That's why I'm a professor of computer science, not in engineering. So loneliness, you can see this poor lonely cell dies in the next cell because it's only got 2 neighbors, it's got less than 3 neighbors. There's then just basically 2 other rules that you also die from overcrowding. So if any cell has more than 3 neighbors, then it dies from overcrowding. And then finally, the third rule is if there's precisely 3 neighbors to a cell, then you get birth, the cell reproduces. Now, why do I like this? Well, because the point about these 3 very simple sets of rules in this universe played across this sort of checkerboard is it actually leads to some quite complex things. And that's, of course, why Conway was interested. It's known as the sort of cellular automata. And you get these objects appearing in this sort of universe. And this is one called the glider. Now, the glider was discovered, in inverted commas, by Richard K. Guy in 1969, before life was even published.
Sorry. The slides
is it again? You can't see.
They're not going on.
That's amazing. I can see very well.
I'm sorry.
Let's just see what's going on when I share, if I've ticked something funny. Okay, I'm going to untick that. Try again. Okay. Stop sharing. I'm sorry. Let's try that again. How about now?
Yeah, we can see the video.
I hope I don't have to reshare every time. I mean, it's going to slow things up.
Do you want to just check you can go forward 1 and back 1?
Yeah, let's see. You see that?
We're on birth, yeah.
See that?
Yeah.
Very good. Good testing. I can see you're more involved in engineering and safety checks. Yeah, definitely. That's why you're a professor of that. Right. So in the glider, for example, it's just define these very simple rules. And what you get is this pattern that moves across the board. So we're moving the board in the background to show this. And this is one of a number of patterns that emerge in this game known as spaceship. But what I find fascinating about this is Conway, you can think of him as the sort of, I chose this picture of him because he looks quite godlike here. And you can think of him as the god of this universe. He created this game. He defined the rules by which this universe operates. But he's not omniscient in the sense we might simply think of God as being. Because here in this example, which is sort of moving very slowly, something funny going on today, is a loafer. Now, this pattern wasn't discovered until 2013. Right, so despite the fact that the rules of the game haven't changed, this one should be moving slowly to the left. Despite the fact that the rules of the game haven't changed, there's patterns that can appear in this universe that the God of the universe wasn't aware of, despite they created it. And this is, of course, because of emergent behavior. And why I find life so interesting is this emergent behavior is occurring with the simplest of deterministic rules. This isn't to do with uncertainty, probability in the sort of sense of something stochastic happens. This is to do with a deterministic universe with simple rules, but just through lack of computation, we can't discover these things. And to me, this is at the heart of the problems we face when we're trying to go from, say, the physics of the universe to trying to understand the sort of things we care about in the universe. And the sort of things we really care about is a volcano going to go off? Is there going to be a hurricane? Is there going to be an earthquake? What's the effect of climate change? How can we intervene in this system to reduce the amount of carbon we put out? Will this bridge fall down? And these are all the consequence of many of these rules coming together to form physical behavior. Now, that's what fascinates me about this domain, and what makes me think when you're faced with a challenge, you could try and infer it all. You could take the Navier-Stokes equations and you can compute a way to try and see exactly what's going to happen to the atmosphere. And then you can put alongside it your understanding of the oceanography and whatever else. But the amount of compute you need, I mean, given that we didn't discover that loafer thing till 2013, and given that Navier-Stokes is a lot more complicated than the rules of games of life, this is where data comes in. Because data is giving you a crutch. It's giving you a crutch that is emerging from the fact that the world around us is moving forward. And data is the result not of a simulation, but out of what actually happens. And I think the really interesting challenge is, how do you combine that physical model that you have, your understanding that we place in the physics, with the data that we have around us? And that, to me, seems like a key challenge of data-centric engineering and machine learning in the physical world. So I include this picture because up until a year and a bit ago, I worked at Amazon. And the reason I went to Amazon is I was very keen to see how machine learning plays out when it interfaces with the real world. I also include this picture because in the background, that building is actually Amazon's building in London. But in the foreground, this is Holborn Viaduct, and it's a statue of science. And I noticed this statue coming out of the building. But what I love about the statue is, I think it's 19th century, this viaduct is built, this statue is created, what it's holding. And what it is holding is the centrifugal governor, or Watt's governor. And this, to me, is also going right the way back to this strong connection between machine learning and sensing systems and artificial intelligence and engineering. Because, of course, Watt's governor is an early sensing system that he incorporated in an engine. Actually, it was Matthew Bolton that spotted it and told him about it. And Watt then incorporated it in the engine to do monitoring on that engine to ensure that the engine didn't overspeed. So in some sense, we can go all the way back and see that this is the first example, or one of the first examples, the first example I know of data-centric engineering. Because although this is a physical system, what's going on is it's sensing the speed of the engine. It's a speed sensor, and it's reacting to that speed of the engine to close down the throttle when the engine goes over a certain speed, thereby regulating the speed of the engine, thereby ensuring that a human being does not have to be beside the engine at all times, making sure it doesn't overspeed. I mean, of course, it's a fundamental object in another ways, because it leads Maxwell to start writing his famous paper on governors, which is all about feedback control, which is one of the major ways that we introduce data into engineering already. What I want to really talk about today is, well, how have things got different? What's new? Because I think it's a totally valid question to just ask, what's new about data-centric engineering? Why is this any different? If Watt was doing this back in sort of, I think it's the 1780s or late 1770s that they would have seen this, why is there any new phenomena going on? Because I think fundamentally, the things that are going on are very similar. Encoded in this governor is a set of weights on the balls, which in effect reflect the governor's understanding of the engine's dynamics. All the settings of the governor are, just as we do in controlled engineering, where we look at the transfer functions and so on and so forth, are an attempt for the governor to represent what it needs to understand of the engine to respond in the right way. So that's very, very close to the challenge we face, where we have a physical understanding, we have data, we don't necessarily have a lot of compute. The governor isn't going to compute the whole of what the engine's doing, it just computes the necessary part. And what can we do when we combine those things? Okay, so this is just the mechanism itself. So, you know, relatively simple, but beautiful. So I think there's a big gap between the world we see in data science and AI as practiced at the moment and what we want when we're practicing that world into the physical world. And that gap is very associated with the fact that in data science and machine learning, what we're typically doing is doing data-driven modeling, but with the minimal number of mechanistic assumptions we can afford to get away with. So we're in this region where we're data dominated, where we can afford to get enough data that we just interpolate between different parts of the data by smoothing. Now, smoothing is a mechanistic, a physical assumption, right? So smoothing is coming from some underlying assumption about like diffusion or something like that. That's why we see it so much in the world. But it's a very weak one. We don't include things like resonance. We don't include deep understanding of the Navier-Stokes equations. But when we want to go to the physical world, if we're doing climate modeling, like it's no good just looking at what data we've got about climate over the last 60 years, when we're trying to extrapolate into a future world where we've never seen the climate we might be driving into. How can we know the interventions? We need that physical understanding to be combined. Other domains, causal understanding. What's the causal mechanism? What does causal mean other than some sort of abstraction of the underlying physical laws? So I think that these areas, there's really fascinating areas at the interface. To me, everything interesting happens at the interface. Now, I dread to think whether this video is going to work, given that nothing else worked. But let's give it a shot. Maybe I'll have to restart again. But this video here is when I was at Amazon. Is that actually coming out, Lizzie? You're nodding. Okay. So this is the Amazon Prime Air drone. I've shown pictures of people who were in the main team. My team was an assistant team. This is Gur Kim-Chin, Paul Viola, and David Morrow, who were actually part of the main team that built this. The reason I'm including this video is because this system has a control system in it that has allowed it to do what it just did. And I'm going to rewind and show it again so I can talk about it as it does it, which is go from vertical takeoff and transit to horizontal flying. Now it's doing it now. Now it doesn't look particularly spectacular to you perhaps, and it's designed not to look spectacular because the aim is for that to be done as safely and efficiently as possible for this drone. It has to be able to do that because it requires to be able to go a certain range to make it commercially viable. And I'll come back to that range. It's in the notes, the range. But isn't it beautiful once it's flying? Of course, it has a much lower wing area than a classic fixed wing aircraft because it doesn't need its wings for lift. It's going to go back transit again to vertical flight in a moment, but it looks like a TIE fighter when it's flying. I tell you, the first time I saw this video, I was quite emotional because it's so beautiful and we'd worked so much on it. Now, looking at it as it's going up, it's transiting to vertical now, and it will drop down and land. Now, the complexity of doing that, it's all in the transition for those of you who really, I'm not an aerodynamicist. David Morrow, who's at the top here, was an aerodynamics guy. Paul Viola is actually a famous machine learning researcher, was the technical lead in that team, and Gur was the sort of manager who was worrying about the structure all around it. But why I find that example interesting, it's the thing we worked on in Amazon. We worked very closely on the control systems for that, using ideas that I'm going to outline as I move towards talking about the supply chain, but in a very similar way that's closely related to that sort of, it's the modern example of the sort of what's governor. But of course, it's being done through compute. And instead of having heavy, massive balls wavering around, we're using machine learning models integrated with classical control techniques in order to deliver that. Unfortunately, I think I can't say too much about the details about how we do that. I was never sure what I was and wasn't allowed to say. In the notes, you'll see I've put a load of specifications, which I know I'm allowed to say because there was a talk by the CEO of Amazon Consumer, which said all those things. But before he said those things, I wasn't sure whether it was secret or not. But it included things like building electric drones that can fly 15 miles and deliver packages under £5 to customers in less than 30 minutes. And that was the specific target for this drone, right? That's why you have to go vertical and horizontal, because of the range and because of the load you're looking to carry. So that's what I love about these physical world problems. It's very real. Like, it's not like we want an accuracy of 49%. It's like, don't care how you do it, but you need to be able to go 15 miles. You need to be able to deliver this package of up to £5, and you need to be able to do it in 30 minutes. Otherwise, this isn't commercially viable, is sort of the situation. So that's what that video says. I'm not going to play it. There, I just included that picture of the thing. The first time I saw that, I was at the Secret Drone Center in Seattle. And of course, it's kind of gobsmacking when you first see what they're aiming to fly. And then when you see it flying itself, yeah, like I say, I think it looks like a TIE fighter. So that was like a great moment for the team to be even involved in working with the team that were doing that. But, you know, we were only sort of 3 or 4. There was a very big team building around that. But I want to go sort of from that system to something that's much closer to the sort of AI software systems that we're building today, because another area we ended up working in at Amazon was the supply chain. And I'm fascinated by the supply chain because it is an interaction between the physical world and machine learning, but it's not so directly the physics of flight or the physics of the atmosphere. But there is a sort of fundamental underlying physics of purchasing. So in Amazon, it does automated purchasing across the whole network. So there's a large-scale systems that are interested in understanding what the optimal stock is, and that's all automated. And again, I have to be careful about how much I say about how they do it, but so I've just come up with trying to forget about how they do it and give you an example of how this might be done. And what you're interested in doing is working out what your optimal stock level is. Now, you choose this optimal stock level based on what you think the demand is going to be for whatever the product is, and what you think your supply is going to be. So you're basically operating as capacitance between suppliers and demand. I had an amazing colleague, Narayan, who used to say, he said this most wonderful thing to me about what the supply chain was. He was a supply chain expert. And he talked about, he was from Bombay, but he was originally Southern Indian. He talked about being in Kerala and being on a boat. And there's a guy selling coconuts from the seashore, from the riverside. And basically you go up and you buy a coconut. And every time you buy one, he goes up, picks it, comes down, sells you the coconut. When that tree finishes, he moves to the next tree down the river and does it there. And then Narayan said to me, and Neil, he had a wonderful deep voice that I can't do. He said, Neil, the magic of supply chain is making it look like everything grows on trees like that. So in other words, you don't want to wait sort of 2.5 years for someone to make the laptop for all the components to get your laptop. You want to order it and it appears tomorrow. And the way, of course, that's done is by putting capacitance in the system, holding stock. And it's in Amazon's interest to hold the right amount of stock to balance between how much it costs to hold that stock and deliver to people in the, the next day or whatever they're trying to do, while saving as much money as possible. And so you have a number of components coming to that: what the demand will be, what your supply is likely to be, how long it's going to take your suppliers to deliver, what the cost basis of those items is, how much they're going to cost to store, how valuable they are to customers. And then you end up sort of computing what your expected stock should be, and then you end up making purchase orders. Now, if you're an engineer, you will, as I do with my mechanical engineering background, see this immediately as a control system. You're trying to you're actually putting out orders according to input signals. But, I don't think that the company saw it so much as that, because this domain tends to be dominated by operations research people who are interested in things like minimizing the costs of this system. So OR people tend to work with money instead of probabilities. In machine learning, it's often probabilities, and in OR, it's money. But what you end up with is what I would say is a monolithic system. So what you end up with is a piece of software that tries to do all of this. And this is the sort of typical thing that supply chain software sellers would have sold. Narayan used to work for one of them, which tries to bring all these things together and tries to help you in managing your supply chain. Now, famously, many, many companies manage their supply chain on Excel, including major companies, in an effort to try and make it as flexible as possible. But you might think that, certainly Amazon, when it set up its supply chain initially, would have had one large piece of software that was trying to do that all in sort of Java or whatever the code of the day. So I'm drawing that as having these separate components as part of this monolithic system. Now, Amazon, and a major reason I wanted to go there, actually is famous for doing a particular thing with these monolithic software architectures. It wasn't in the context of the supply chain, but it was in the context of the web server that they built. So initially, Amazon had a web server that was doing something like this in one piece of code. So it's like a large binary code base or whatever, and they were trying to scale that. And around about, I guess, the turn of the millennium, as the demand on the website went up, and I spoke to the guy that did this, a guy called Charlie Bell. There was a system called OBIDOS, and this OBIDOS system was sort of straining under the demand to run the web server. So what Amazon did, and Charlie is now the technical lead of this section of the company, is they said, okay, can we do this in a more scalable way? A way that means that as demand increases in terms of compute, and again, we've got supply and demand stuff going on, but here the demand is for compute, we can scale our computability instantly in order to respond. And what they chose is, and using technology, some of which were developed in Cambridge, was what they call a service-oriented architecture. So a service-oriented architecture is where you take that monolithic system, you recognize that there are underlying components, and each of those components itself is doing a single job. And you write each of those components as a separate so-called service. And these services call each other. So in this case, I'm showing it feeding through in a certain way. We could link it in a different way, but the particular notion I have here is that there's a demand forecast. And then what I'm trying to show here is, because I'm thinking of this as what's called a streaming system, is joined to a supply forecast. And they are joined to the cost predictions. And then they are combined in order to make a purchase order. So you end up with a decomposition of this problem. Now, the interesting thing is, of course, this is a sort of virtual decomposition that is also related to the physical world. So if we look at what's engines, we can see the parts, we can see the condenser, you can see the cylinder, you can see the governor. Here, this is a conceptual virtual decomposition. And this is the sort of thing that tends to be emergent in software systems now, is we end up decomposing them in certain ways according to what we think the best way to run the thing is. Now, that decomposition turns out to be at the heart of all modern software. So this idea that you're going to build software systems by decomposing them into single small parts, the nice thing is now you say to one team, you say, go away, you own that part, you own the demand forecast, you own the supply forecast. You are responsible for ensuring it's bug-free, it's available, and you're responsible for ensuring the quality of its outputs are sufficient that we can use them. Now, of course, that service can be used in multiple places. So you might want to use that supply forecast for your buying, but you might also want to use that supply forecast for, I don't know, your projections about how many staff how many staff you need on delivery, how many trucks you need to provide. Your demand forecast, similarly, you might want to use that for your last mile delivery. How many people do you need to bring on a last mile delivery? And now you can use these services in multiple places. Now, that's causing this proliferation of these architectures, which are called service-oriented architectures. And the reason they work, and the reason they escape what is known as the sort of mythical person month, is because of separation of concerns. You have separate teams worrying about each of these components. But I think the thing that is majorly happening in the software systems, therefore the AI and ML systems, therefore the data-centric engineering systems of today, is that these systems become so complex that we lose track of what they're actually doing. And I really love this term. I had this concept in my mind for a long time, and then I read this blog post by Jonathan Zittrain where he called this intellectual debt. Now, the notion here is that you're just creating a supply forecast, a demand forecast, and so on and so forth. But someone else starts joining them up in these interesting ways. And as they do that, they create something that you no longer understand. And it's operating in the real world, doing all sorts of clever things. But when it goes wrong, when you get the email from Jeff Bezos saying, why was there a tailback on Route 66 with our trucks, you know, in Phoenix? I don't know if Route 66 is near Phoenix, but imagine it is. You know, and you know what went wrong, and you've got to explain it. You realize I don't understand my own software system. That's an artificial example, but you can imagine the type of thing. Don't think that that's what happened in Amazon. I never got that email from Jeff. So we can contrast this with other notions such as technical debt, which is about the quality of the software you've built. But I think even if you are on top of, you've got really good software, this is still a problem because of the separations of concerns. So I think of this technical debt is this alternative thing in software where I build this too quickly and it needs a lot of maintenance. So that's about the inability to maintain your complex software system. Intellectual debt is about the inability to explain your complex software system. Okay, so how does that relate to perhaps some domains that we're more interested in as we get to the physical world? Well, kind of exactly the same thing is going on. I really, really love this image, although it's probably a bit small here. What it's trying to show is all the different modes in which the UK Met Office runs climate and weather models. And what it's showing is the different forecast lead times, and then it's showing the spatial length. So it's showing, it's taken off one of their websites. It's showing the sort of temporal resolution, it's showing the spatial resolution, and these are used for, you know, like if you are into this stuff, you'll know some of these models. But their key idea at the Met Office is that they run all these simulations on one model, that they have one sort of global model, they just run at these different resolutions, which is pretty extraordinary and I think fairly unique to the Met Office. So they do not do the service-oriented architecture in the way that I've just described. But one of my arguments is that actually we're going to need to do the same thing I talked about for the web server at Amazon and for the supply chain at Amazon with the type of simulations that we want to do here. If we're going to, you know, I don't know what digital twins are, but if they are anything, then I think they are the need to do exactly what I described with those Amazon services, with some of the services that will be operating within the Met Office model of the climate. That sometimes you might want access to their atmospheric model, sometimes you might want access to their oceanographic model, their, I don't know, whatever models they have in there, and you may want to use those models in other domains. And if we're going to build large-scale digital twins that are offering at different granularities and so on and so forth, we're going to need to turn what I call turning those models inside out to expose all those services that should be in there and away from these large monolithic services. We're also going to be in trouble because running some of these things is incredibly slow. And one of the really interesting things you find as you start to simulate is you don't always need to run things. So the big picture I have for machine learning in the physical world, and this is certainly not the only game in town, but it's a pretty big game, is how do you interact between simulators of different granularities operating on different parts of the world you care about. And this is physical world, this is data-centric engineering, this is Amazon supply chain, this is a bunch of different areas, and interact that with real world data. And, you know, you might not be surprised to say that I'm going to say that to me, the route is a machine learning route, but it's what we call machine learning, but what is more traditionally called in UQ a statistical emulator. So I think the big role for machine learning and data-driven modeling here is, and you've already had a talk in this series from George Kanikadis about emulation, and you know, I think I have a paper co-authored with him where you know, our people work together and exactly in this sort of domain. And the aim is that you start building statistical models that allow you to reconstruct what these simulations say. Now, why do you bother doing that when this is clearly going to be, this is the correct thing and this is some sort of reconstruction? Well, this is much faster to run. Okay, and it can also start doing some cool things, like it can also assimilate data from the real world. So it can start to say, where is the simulator departing from what's going on in the real world? Now, I can't say too much about the Primaire example. I also worked on Formula One in examples that I can't say too much about. But in all of these cases, you have a situation, if you're looking at aerodynamics, where you've got the ability to run computational fluid dynamics, you've got the ability to go into wind tunnels, you've got the ability to fly the damn thing or put it to the test track, right? And what you're interested in very much is what's the most efficient use of our time and money in order to get the most information we can get about this device, particularly if you've got a rapid turnaround, as you do like in Formula One, where you're interested in trying to get the parts to the track, the best parts of the track, you've got limited testing time as rapidly as possible. And in these cases, the emulators can really give you a clue as to what's going on, because they don't just model what the simulators are saying, but if you do multi-fidelity emulation, which is some of the work we did with George, you can start saying, what is the right thing to do? Is it this granularity of simulation? Is it the real world data that you need? Is it from the sort of higher fidelity simulation? Should be running a higher fidelity simulation? And of course, the answer to this is contextual. It depends on what your question is. So you cannot do this once and for all. You can't just do this once. You have to be able to deploy and build these emulators on the fly and design them to answer particular questions. Now, that comes back to the sort of, so in the case of Amazon, we would be doing this across operations research models, optimizations, and machine learning models. So you can even do emulation of machine learning model. You can have a machine learning model under the hood, but you can build around it something that's a bit more interpretable. That gives you interpretability. So how does that relate to what I said before? Well, if you've got your service, if you've got out of this monolithic world, then you can do this process of what I call deep emulation, where you start to sort of on the fly deploy emulators for any one of these services. And if it's necessary, you start connecting them up. So you might want to avoid this chain overall. If you're going to simulate the system, and you do run simulations for this as well as running it in the real world, you might not want to run the computationally expensive simulation. You might want to run your emulation for part or all of this instead. And that may be sufficient for answering the question you're interested in. So the sort of basic idea is that in your large-scale climate simulator, if you're interested in, you know, in 20 years' time, how many hurricanes are going to hit Key West, right? If that's what you want to estimate, well, maybe you don't need to run the simulation across the whole planet. Maybe you can emulate parts of it. I don't know. But the idea is you can answer that sort of question quicker. Just in the same way with the game of life, you don't have to run the whole game of life before you see that pattern. So how are we doing this in general? Well, there's lots of data-centric engineering work going on in Cambridge, but I feel compelled to also advertise the Accelerate program, which is about machine learning in the physical world, but in a sort of different domain, where we're trying to accelerate scientific discovery with machine learning in very much the way I described. So just as for data-centric engineering, there's this smooth border between engineering and science, particularly if you're in the environmental sciences. So one of the things we'd like to be able to do is, just what I said just now, is augment environmental science simulations with machine learning models to able, or the motto I used to use in Amazon is we want to be able to do more experiments, where when I mean experiment, I mean running of the simulations to answer more questions quicker. Sort of increase the speed of simulations by using emulators appropriately in order to be able to ask more about the system of interest. And it's one of the things we're looking at in the Accelerate Science program, which is a broader program about trying to, just as the data-centric engineering is bringing machine learning, AI, data science to engineering, it's doing the same thing in the physical, environmental, and biological sciences. And the other thing I want to sort of talk about, because you're sort of like, well, this is all very well, but you haven't really said anything technical about how to do it. So I also just wanted to advertise, and again, it's in the notes, there's the link there, you can link directly through to this course. So in anticipation of this lecture, being invited to give this lecture, last year, myself and Carl-Henrik Eck, we created an 8-week course on machine learning in the physical world that tries to introduce a number of these concepts around emulation to computer scientists and, well, people across the university this is open to, where you can start seeing how these techniques build in the parts. I should say that the bit I'm proposing here, where we can dynamically go in and deploy emulators as required on top of an existing software system, is not something that is by any means, shape or form complete yet. We have a number of research projects, first of all, looking at how do we encourage software engineers to build these complex systems such that this structure is exposed, right? So the fascinating thing for me when we were working with Prime Air is we were working with engineers that controlled the entire physical system, the amount of testing they were doing on that thing. They controlled the end-to-end pipeline of the software that runs that drone for very good reasons, for safety reasons. So we didn't really have much trouble when we were having to drop in and wanting to emulate certain parts, right? We just spoke to David Morrow, who was, our contact, and it was all done. And we were able to do very advanced emulation techniques. Contrast that with a situation where each of these components is being deployed by a separate software team that tries to talk to the other software teams as little as possible, and also doesn't tend to share what's going on inside or what their inputs are necessarily. And you're trying to emulate in that domain, right? And they do that for good reason, because they need to deploy these things quickly and move on to the next bit. But unfortunately, that means that this equivalent type of deep emulation thing is very, very hard to do. So another thing we're working on the Auto AI project, which is a subject of the Senior AI Fellowship that Lizzie mentioned at the beginning, is how do we build software in such a way that this sort of what I sometimes call this tube map of the data flow through the system is exposed, and we could rapidly deploy emulation in the relevant parts. So a sort of big project with big ambitions that we're not going to be there for a while yet. But, and many sort of like, well, how do you do that? And how's this going to work? And so on and so forth. We're clearly not going to do it all ourselves. I'd like to also use this opportunity to sort of invite other people to get on board with this agenda. I mean, I think just by the fact that you're here, you broadly are on board with this agenda, because I think there's a lot of really big and interesting problems to solve. And I'm going to sort of stop there and see if there's time. Give us some time for questions.
Thank you very much, Neil. It's a fascinating talk, and yeah, plenty of time for questions. So just give a minute to for those to come in. Please type them in the chat. I don't know if you can see already, Neil, the chat board.
So yeah, I can see one from, and I guess if people put there, because they can be anonymous. So I'm going to announce the names if they've chosen to put their names. How would you distinguish the theme of your talk about data science in the physical world, the long-established engineering disciplines of control and control theory? Yes, okay. So now at this point, I have to go back to my shelf and find potentially a couple of books. Well, so one of them could be this one. So here we go. Norbert Wiener, A Life in Cybernetics. Vina, Cybernetics. I think probably the most important technical book that's up here is this one, Stationary Time Series, The Extrapolation, Interpolation, and Smoothing of Stationary Time Series. It's known as The Yellow Peril. It's the book Norbert Wiener wrote in the Second World War to help people track and shoot down aircraft with radar. So I really, it's great. I love control and control theory and stuff, but Wiener was establishing the domain of cybernetics, which is actually the domain I'm in. So what actually happened is there were certain things we could do and do theory for and deploy with the technologies of the day. And we've done them and we're on top of them. But there's a load of other stuff in this book that is not about feedback control that is missing. And in a very real sense, because of the wide availability of compute and the very, very large availability of data that just was not there in the 1940s when they were establishing the field of cybernetics. And by the way, that is the book that describes how Gaussian processes work, right? So it's in time series, not spatially as we're using them today, but Wiener is sort of very much the father of Gaussian processes. So, Wiener knew everything, and we're still trying to work out what he was talking about and how it should be deployed in the context of the data and the compute that we have available today that he did not have, in his time. So I think it's just about the things are closely related. The traditions are slightly different. In practice, I think one of the things you see is that control theory has worried a lot more about worst case performance than machine learning worries about, right? So that's how I would put it in a machine learning sense, that machine learning tends to focus on average case performance, not worst case performance. And that's severely problematic when you look at some of these domains. So average case is fine for supply chain because you're just losing money if you get it wrong. It is not fine for driverless cars because on average you kill quite a few people. So we see that sort of things emergent. But I think that to me, getting back to, there's some things that were bad about the cybernetics community. Wiener was a particular character himself, and there were some sort of social problems between different big figures in that community. But if we can get back to the spirit of what that community was trying to do, where it's bridging right across from engineering to notions, the UK equivalent of that community had Alan Turing in it, and to psychology and to statistics, to physics, then we're going to solve these problems a lot more quickly. And I think that we have to respect those existing domains, but we should not believe that they are somehow the canonical way of the things will be in the future. We need to do as much as possible to learn the lessons from those domains and carry them forward to the challenges that we can now address with large data and big compute.
I think there's some questions, some kind of career development questions coming in, but there's another question in the chat that's a bit more to do with what you were just talking about. Not in the Q&A, it's in the chat. So it's about wondering what the deployment requirements are for the I'm guessing for the drone.
For the drone, I wouldn't know all the details, but obviously it was a fascinating time, I think, when worrying, disturbing time. When 737 MAX had problems, I was still at Amazon, and I was at a meeting where a number of the Prime Air people were, a lot of whom were ex-Boeing, and we were just talking about, we were examining that forensically to see how culturally things might have gone wrong. I don't want to say too much about what we thought had gone wrong and so on and so forth, because of course the constraints on what you can do and how you do it. And actually Amazon, I really like this side to it. The engineers were not separated from that. They understood that the whole project was contingent on deploying a safe drone and what it would mean for a large company to have those things, causing any problems. And so you've got I think the really interesting thing that you've got in this domain at the moment, you've got whatever the regulatory law is, which is sort of one thing, but technology is moving so fast, it's sometimes moving ahead of the law. And although like CAA and the FAA regulate drone flights quite tightly, I think if you map it onto things like driverless vehicles and some of the things you look at that people have been doing and have on the road today that I think are ethically highly dubious, I think that there's a responsibility on engineers, and certainly I always felt that that was the case with the people I was working with, to worry about those things as well, that it wasn't sufficient to say that the law will allow us to do this. You actually had to go beyond that and say, yes, but is it what we should be doing? Is it just because the law hasn't had a chance to see this and realize it needs regulation? And that's not just true, and as we're deploying these physical systems, I think that's even, well, as true. It's true for different reasons as we deploy these systems sort of, you know, in social media, advertising and everything else. So yes, there was lots that, you know, was not my day job to deal with, but I know how seriously it was taken.
If we can move on to some of the career questions now, if that's okay. The one that got rated up first is what kind of background is expected from someone who wants to join the accelerator program?
Right, so Accelerate program tries to cater for all levels. So our idea is that there's just no possible way that this can all be done by data scientists and machine learners and, you know, people like myself who've spent years doing this. That what we really need is domain experts to be understanding what the possibilities of these new group of methods are, what the limitations are, because we think those domain experts are the ones who are sort of probably most, what would be the right word, they're the ones that are going to account for all the issues within that domain when deploying these things. And if they can characterize the data science techniques well and what they can and can't do, they'll be the ones that are best placed to understand when they should and shouldn't be deployed. There's a big problem at the moment that these techniques are being seen as if they're magical, that they can do things. I mean, they can do some pretty amazing things, but the problem with that is like, what are these quotes about, like, to any sufficiently advanced technology appears to be magic to a civilization that doesn't understand it. Well, we need to move away where this is, you know, if there's a sense that it's doing something magical, that's severely worrying, because it's not. It's just data-driven modeling with slightly different emphasis and large data and compute involved in ways that hasn't been before. So there's particular pitfalls with it. And I think that the big idea with Accelerate is to, yes, on one end, advance the techniques we have, make them better, do the research on those questions, but follow the spectrum all the way through to the other end, which is to take people who are in, say, the physical sciences. In fact, we're going across the board. We've got social scientists, humanities people, etc., and put them through courses on data science that aren't just about this is how I run a neural network, that try and give them some of the intuitions and the basic skills so that they can integrate that work within their PhD work. So keep an eye out. It's advertised when we're launching these courses. We're on our third. We do about 25 students each time, and we're looking to turn that into a community across the University of Cambridge. I mean, the idea would be to impact outside Cambridge as well, but we're also trying to sort things out here for delivery on that.
So that might lead nicely into the next question, which is what should a budding data scientist enthusiast do next to master expertise in the field?
You know, I always
from an undergraduate perspective.
I think that it's a great question. I guess it depends a little bit on what anonymous attendees' current degree program is. It depends where you're coming from to a certain extent. Like, if you're in statistical sciences or you know, certain branches of information engineering or computer science, you can sort of start playing with the methods and you'll have opportunities to do that. But quite often you might find you're in a domain where you know, I much prefer the idea that people get excited about a problem and really want to solve the problem. And then they realize that maybe these data science techniques can help them solve the problem, but they're very serious about solving the problem properly. And they're not just like unthinking about how they deploy these things. It really feels to me, you know, you can probably sense from my talk that I love old stuff. You know, I like James Watt, I like Bolton. That's why I did mechanical engineering. I like Norbert Wiener. But, you know, it's nice to like all those things. The reason I like them is because it's such an exciting period of discovery when they exist. I like a little bit less the bit where I read about how much riding around Cornwall they had to do on horseback to persuade miners to buy their engines. And I really think, wow, we're in this sort of world where we get to be the Boltons, Watts and Wiener's of this new possible world of possibilities. And we don't have to ride around horseback around Cornwall. But what we do have to be is just as serious about as they were. What I love about them all is they took the outcome and the applications of what they were doing extremely seriously. It wasn't technology for technology's sake. And there's far too much technology for technology's sake going on in machine learning at the moment. And I think that if you are a budding data science enthusiast, don't become one of those. We've got more than enough of them. You become someone who's really excited by solving a challenge, something new that we can do today that we couldn't do before, and getting serious about the techniques and how to deploy them.
Great. There's a question about emulators there at the bottom of the chat. So it says, how do you see emulators working in applications such as engines and turbines, where performance is critical in service? And would ML still work and predict potential failures?
It's a great question. And I think that there's, and I'm not an expert, but here's my loose sort of opinion when I think about the governor. And I think that, in some sense, embedded in the governor is an emulator, right? So at the heart of the governor is a prediction, all the setting of the weights is that there's an engine response time to a move on the valve. And you don't want to sort of immediately, and actually it used to come up, it's called, in supply chain, it's called the bullwhip effect. There's also a response time of the whole supply chain to you changing your order. And if you ignore the dynamics of that, you end up with a resonance at the supply end where you one week order 1,000 items and the next you order none and the next you do 1,000. So I'm fascinated by that connection behind that sort of effectively seems to be what's going on in control at the heart when you look at the transfer function of the control of it. And the nice thing then is in the linear system, I can prove things about what that's going to do. But as we move away from that into nonlinear systems, there's a feeling that we can't necessarily prove that. But having said, I think there's all sorts of interesting ways you can go. So I had the pleasure of meeting Mark Rayburn of Boston Dynamics and talking to him about his dog robot, and that's all classical control, but it's control is being switched in contextually. So everything, so the whole art about it is how you build this. I thought of it, I'm not sure if this is the right way of thinking about it, like as a hierarchy of controllers that get switched in the right way. And I thought that was a really interesting example of something where you've got something provable about how this system is going to operate. And it's doing some sort of control that is well out of the regime that we might normally expect. I don't know necessarily. I think that there's an interesting question: where does the boundary of the emulator stop and the controller begin? And I think that it doesn't matter. I mean, really, it's like it's going to be domain dependent. And I think that as good engineers, we're going to have to select that answer according to what the domain we're in. Is the emulator a tool to help you design the controller, or is the emulator, does it become part of the controller? It's going to depend on the risks involved in what you're doing. As you mentioned, like aircraft, that's clearly one where you're going to want to be a bit more conservative, versus other domains. So I think it's super domain independent, and I definitely don't want to say that there's a one-size-fits-all answer here. What I'm trying to say is, there's this conceptual way of thinking about what you're doing, where you can borrow all this material from uncertainty quantification, statistical emulation, and in some cases, if you design particular emulators, that emulator is going to be able to go into sort of safety-sensitive domain as well.
If you have a complex system where your understanding of sort of the interaction isn't necessarily complete, how do you go about kind of targeting what your different bits of the emulators will be doing?
That's a great question. And I think that and it's another one of these ones where different domains have approached this, I think, in a way that actually turns out to be quite similar. The econometricians that we used to work with used to call it bridging. So I think the classic thing that would come up, and this is why, although supply chain was harder in many ways, it was sort of much more interesting in some ways, because you get the situation where the vice president's saying, why are we under stock on this item? So, you've got someone who's sitting there, give you the picture, every week someone's sitting there looking at their entire Amazon worldwide supply chain and finding, that we're short on televisions in Germany, and then wanting to know why, right? And that's the intellectual debt problem, which you're really hitting on, I think, there, Lizzie, is you want to be as soon as possible. Is that because our forecast was under the actual demand? Or is it because supply was under our actual, or is it because we misunderstood the cost basis, or is it something else? And in econometrics, they do something they would call bridging. But I would just, as far as I understood, that was just linearization around the operating point. So you look at your overall complex system, you look at the operating point that you were, because this is clearly a nonlinear thing, what your stock ended up being versus all these other things. And you just fit a linear model in the region around where you were operating. And then you lose that linear model to sort of, you've got now sensitivity according to your inputs. And that's, and I may have got that a little bit wrong, but that's as far as I understood what was going on with bridging. But you could view that as an emulator, right? So you can view that as I've just fitted a linear emulator around this operating point. Okay, so again, you can see that this framework is, if I can fit it, it is a statistical model, or one that is approximating according to the gradient. You can see it fits sort of broadly within the framework. And the sort of problem that we would have with that is, once someone had set that up, that was fine. But if someone asks a new question about something in the system and you don't have your linear emulator deployed across that subpart of the system, you can't give your answer. And you can start seeing this as you sort of think of things like GDPR and the need to be able to explain the decision making. I think one of the things that people are missing is it's never going to be, or it's almost never going to be, the decision that a single model made. So people are doing things like linearizing the decisions of a neural network, which is very similar to the bridging. Of course, they don't reference the bridging literature because that's the way things are. But they're doing that linearize around the operating point. But I think that in real world, very often it's going to be a system that made this decision. And you're going to have to linearize around more than that neural network, what the neural network's inputs are and its output, the upstream and the downstream systems. And that's why I think that this need for this understanding the underlying structure of whatever system you've built is there, both for regulatory reasons, but also for the explanatory reasons. I think it's not good enough to do this thing we do in engineering, where when someone who's not an engineer asks us what's going on, we say it's too complex for you to understand. That's what's got us into trouble. And we really need to be able to explain these complex systems to the people who are on the hook for when they go wrong, and so that they can understand the seriousness of that effect.
I'm just surfing the questions. They've got a bit more serious.
More serious? Oh dear, that sounds ominous.
There's some particular ones about emulators which we might stick on if you fancy specifics.
Yeah, go ahead. I'm happy to do anything. Ask me anything.
Would an emulator for controlling a supply chain in a closed loop be the same or different from an emulator used in an open loop business use?
Oh, I think it's so cool when it goes closed loop. So I want to give a shout out to Rod Murray-Smith up at Glasgow. He's got this whole project, Closed Loop Data Science, that I just think is that I'm on the advisory board for. And I just think, yeah, we're really only looking at open loop stuff at the moment, but closed loop is where a lot of the problems come. When you one of the things, like in the supply chain example, you get closed loop effects because demand is affected by current stock, by availability. So in Amazon's website, if you click on the thing, you'll see something called a promise, right? So the promise is, if you order now, it'll be with you by 8 o'clock tomorrow, right? That's really important. Getting that well calibrated turns out to be a really important thing. It's something we also worked on with emulators. But that promise itself is dependent on what stock levels are. And if the promise goes out, demand will drop. So there is a closed loop effect there. And typically, I mean, in my understanding of most of these systems, whether it's a social media system, so on and so forth, the complexity is such that they're not even doing the closed loop stuff. Now, that's why I really like Rod's project, because Rod is starting to think about what closed loop means, particularly when it's a human and how the human is reacting to the things they're seeing in that loop. And you can see those sort of effects are what's driving society and its response to social media and causing us very severe problems. So I think it's a great question and a difficult one. And I don't know if you sense the urgency in what I'm saying, we need to get on top of this open loop stuff so that we can get on top of the closed loop stuff. Because yeah, I think it's a really great question, and a big problem. And I think it would be there's surely examples where you can start trying to do it already, smaller examples or whatever else. But yeah, a really important problem that I didn't really talk much about.
The link in one underneath it is about how you see model predictive control.
How do I see model predictive control? I guess I don't know enough about the terms and how people think of it. I guess from my point of view, it's all sort of related, right? It's like it's control engineers coming at things the way I would see it from their perspective, while I'm coming at the control side from my perspective, which yes is as a machine learner, but one that grew up as a mechanical engineer and liked all these control theory courses, but hasn't done it at a graduate level. So you know, I think isn't it all of us just trying to get towards doing the same thing and speaking slightly different languages and then going, why don't they cite my papers? Probably, yeah.
Less of that these days, but back to a more general question, if we're okay to carry on for a few minutes.
Yeah, sure.
Great. So this one at the top. The world's full of experimental data about all sorts of things, and it's stored in ways that are difficult to access. So images in hard drives, documentations. What are the best practices for data storage, reuse, longevity?
Yeah, isn't it? It's a great question, Simone. I think it's, you know, this even comes up like, so I even got into a sort of thing like when an engineer is building a new service within Amazon, what should they store? What should they be logging is a question, because what they tend to do is they'll log things that they need for debugging. So the engineer who's building the service will tend to log information they need to prove the correctness of the software as they see it. And that turns out to be quite different, or certainly in a different format, information to say the information that you want for your emulator to check how that service is operating in a wider scheme. And, you know, then I think there's examples. So I have collaborators in Africa. We do this thing called Data Science Africa. There was an example there where people were interested in, they record traffic reports and logbooks. And the idea was to try and assess, I mean, because obviously traffic's quite a thing in say Kampala. And the question was like, are more young people dying from traffic than say a number of diseases that we see as very big problems? It's an interesting question, but people haven't collated that. So a colleague of mine, Michael Smith in Sheffield, he started collating this information and crowdsourcing it. And then the police were like, this is brilliant. So we can start storing all this information electronically. And Michael's like, no, just keep it in the logbooks, because we just don't have any belief or sense that the ecosystem there is mature enough to be able to, you know, it's like better that it's on paper and at least someone's keeping it somewhere than it's being hidden in someone's mobile phone and lost forever. So I think this is a really, really difficult problem. And I think it's this usual thing in engineering where we need to standardize, but if we standardize too quickly, the standard will be incorrect and won't be followed. So I think that the heart of this problem is an awareness that that's a major issue, and then starting to record and monetize what that's costing us. So my own contribution to that is something I call data readiness levels, which is an attempt to characterize the different stages of a data science project. But it really tries to bring out the issues of trying to collate data from where it's stored and getting on top of the legal issues. And just trying, stage C is going from what I call hearsay data, which means someone heard the data exists, so they say it exists, to we can actually access it electronically and pull it into an analysis package or one of these services. And that stage C itself is always underestimated in the projects I've seen. Like, no one ever costs sufficiently for what goes on there. And the other part of it is that the skill set that's required there is very different from, say, the graduate statistician or machine learning engineer who's going to do the analysis. There's a stage which I call stage A, sort of like we've got the data, we've defined the task, someone fit a neural network or linear regression or whatever. And then there's this stage B between, which is checking what the quality of that data was that was stored on these hard drives. So I split it into these three stages that I call data readiness levels, C, B, and A. And the main reason for doing that was trying to surface this issue with, say, management. So you end up sort of saying to your boss, well, you know, this data is data readiness level C, and in our previous project it cost us 3 million to go from C to B. So we're going to need to budget more than that, and we're going to have to ensure that we've got the software engineers, the ethicists, and so on and so forth. Now, it doesn't answer your exact question in terms of how should we store for the future, but I think perhaps because we're not ready to answer that, because we need this to be surfaced as a thing in itself so that people think about it in a structured way, because the answer is going to be quite domain specific, I think. So sorry, I didn't really, it's difficult, I guess, is the answer.
So we're going to get cut off at 15:15, and there's 2 questions left. And I think there's a nice one to end on. And the one I'm going to ask before that is about GPs and neural networks.
Yeah.
So it says, Bayesian neural networks approximate GPs, Gaussian processes, yet are much more scalable. Are GPs going to ever be completely replaced by Bayesian neural networks? And if not, why not?
It's a horses for
apart
courses.
from analytical tractability.
It's a horses for courses. Everyone's, you know, so one thing you can tell, I don't even bother talking much about Gaussian processes anymore. As long as you watch the Bayesian neural networks community, and every time they publish their Bayesian neural network, the next thing they compare to is a Gaussian process, you know Gaussian processes are winning. Right? That's your number one thing, right? Like, no one ever sort of publishes and then they compare to the thing that is the dominant thing, right? There are use cases for Bayesian neural networks. There are scalability issues with GPs, and you know, there are answers. We have a paper with James Henswin and Niccolo Fusi called Gaussian Processes for Big Data that shows how you can go about doing that. The Bayesian neural networks is what I did my thesis on, and you know, I moved to GPs because basically they're really poor at doing uncertainty. And you know, one of the depressing things about a lot of the papers is they show you horribly calibrated error bars, and yet they claim that they've done something. And there's a real problem in that people not using these in actual domains. This is what it comes down to, is that who cares about your error bars? What you care about is the decision. So you don't get to talk about which of these things is better until you've deployed them in a context, whether that context is an optimization or is like a buying decision or whatever else, right? Forecast models in many companies, in many demand forecasts, do percentile prediction, right? So they're doing none of this stuff. They just predict what they think the percentile is, percentile forecasting. And that turns out to be the most sensible thing to do most of the time. Now, yes, so at the moment, Bayesian neural networks can scale, but don't do very good calibrated uncertainties. Gaussian processes can struggle to scale, and also sometimes do very poorly calibrated uncertainties. So it's not really an either or. It's, yes, both of these are interesting tools, and we want to get to a position where people understand, can easily try and deploy the correct one for the correct circumstance, but can actually test them in the downstream pipeline to see if the whole system is working better. You know, personally, I prefer Gaussian processes because they're mathematically more elegant, and I continue to use them for that reason. But you know, it's possible that Bayesian neural networks will end up outperforming them for some reason.
I'm going to try and end on this question. I think there's one more that's come in, and we'll see if we've got time, but I feel it's unlikely. And it is a general question. What area of machine learning do you think is the most overlooked but has great potential?
Oh,
what's my next grant application going to be?
I don't want to tell anyone that. That's the secret stuff we're working on. My next paper. Most overlooked. Okay, I tell you what, I think an interface that must be being overlooked and tells you how much the hype is misplaced. The people who currently still run decision making are the operations research community, operational research, right? They've been around for a long time. I often think, oh, they were like the machine learning of the 1940s. And the amount of interaction you see between operational research and machine learning is absolutely minimal. Yet the goals of, say, things like reinforcement learning. So I wasn't involved in the paper, my group wrote a paper comparing operational research techniques like news vendor problems and these sort of things with reinforcement learning solutions for a number of standardized sort of OR things. But just the very fact that there's so little conversation between the communities and you hear so little at machine learning conferences about OR work shows you there's something wrong. And my personal feeling is that the thing that's wrong is people are not using machine learning in the sort of scale of business decision making that I was talking about for anything other than I've got a forecasting model that feeds an OR model, right? And, you know, people like to talk about end-to-end learning of those systems, and that's nice as well. But you'd be damn sure you do your end-to-end learning in such a way that when you do get that email from Jeff Bezos, because he does send them, that you can explain what the hell went wrong in the system. So I think that there's a lot in that domain that is unexplored and very, very interesting.
I know we said we wanted to get cut out at 1:15. There's a lovely question about non-stationarity and embedding in ML, but I feel it might be tempting fate. What do you think, Neil?
Where is it? How can non-stationarity be embedded within ML models? They mean emulator simulated by the time T not be good. Yeah, so
Can you answer that in 1.5 minutes?
Deep Gaussian processes. So actually, it's a great question, Louis. I think there's lots of ways of doing it, and I think part of the answer comes from what do you know about the non-stationarity? Is it non-stationarity that you're aware of, right? So there's this effect, certainly in the domain I apply, where it's a classic problem in Gaussian processes. You can make Gaussian processes non-stationary, but there's a term that I think is not in general use, but the way I kind of think of it is like non-parametric non-stationarity. So what do I mean by that? I mean that the way you tend to make these things non-stationary is you introduce a covariance function which is non-stationary, and the non-stationarity tends to be centered around a certain position which you can control. So you've got one non-stationarity, but what about the other non-stationarities? You've effectively parameterized a non-stationarity. So I think a really interesting question there is, well, what if you want to introduce this sort of, you don't know when non-stationarity is going to happen. It can happen at any moment. And it's something that I'm really, really interested in. It was, for me, it was a major motivation for doing deep Gaussian processes. So I don't want to say that they're the solution to this problem, but we definitely have used them in emulators for precisely this reason, and they do work. I mean, someone may have done something better. You know, neural networks, people would say that that's what their stuff is doing as well. And yeah, you know, I think to a large extent they're probably right. But lots of, I think, you know, going deep is in effect doing that, because if you sort of non-linearize the input to a stationary model, you get a non-stationary model, right? And if you non-linearize the input to the stationary model in a non-parametric way, you get a non-parametric non-stationarity, as I think of it. That's probably, there's mathematicians dying in the audience with my combining of terminologies in ways that are not allowed. That's it. That was just cut.
I know. Oh, disappointingly, we haven't been cut off, but at least it gives me a chance to thank Neil on behalf of everyone. Neil, thanks ever so much. It was a fascinating talk, and yeah, great answers to questions. And I'll let Mark finish up. Oh, you're on mute.
Yeah, thanks.
We couldn't do a thing without someone being on mute, right? Had to have it. Yeah. Thanks, Mark.
Thanks, Neil. That was absolutely superb. Lots of really good questions, lots of enthusiasm, and lots of good answers and discussion from you. So thanks again. And I think we're probably going to get thrown out in 25 seconds. Yep, we're done.
Good, brilliant.
Thank you very much.
Thank you very much for the invite. It was a great pleasure to have all your time, and thanks for all the attendees for attending.
See you later.
Thank you. Bye.
Bye.